All right, so I guess we are live. So last time we started to work on error correction codes, and we did Hamming, Hamming codes. We looked a bit over Wikipedia, and I also did like the full explanation on the intuition of how it works. So if you are interested in that, you can check that out. And what is left to do for today would be to do the decoding and the actual, um, correcting the errors, right? And since the last time I figured out how to do printf binary, C doesn't have a built-in way of doing it, so just do it bit by bit. I think I was remembering from GDB that you can print binary. Kind of weird that C doesn't have this feature because it's like a really low-level language, but yeah, whatever. I also added this H matrix in the C file because we are gonna need it for today. And yeah, as I said, I went over how the G matrix, like the intuition behind it, why we need it, how you create this code. So you take a single nibble from byte, so that's 4 bits, and you build a byte, so you double the number of bits, but you have some way to correct errors in case they happen. Right. And as I said, for today we are going to implement the decoding part, and that's why we are going to need H matrix for. And as I said, I explained how it works. And while I was trying to figure out how to do the decoding part, because on Wikipedia it's kind of not mentioned, I'm not sure why not. I mean, it says here error syndrome, but it's not really explained how you do all of this stuff. What I figured out was yesterday, or I guess last time, I said that I didn't really understand why they chose to order the columns like this. I mean, as I explained, these are non-zero columns, but I haven't really said why they are in this particular order. Like for this one, it's the I matrix, that's pretty straightforward, but in the first 4 columns, what you need to check would be, let's say we look at this table and we see, for instance, the data bit 1 is 110, and that's the first column. That's kind of the point. Then we have data bit 2 is 101, so it's the second column. Then we have data bit 3, 011 is the third column, and data bit 4 is 111, which is the fourth column, right? And the other ones are just the parity bit, the other one, and the other one. So, if you are not really familiar with these terms, we went over them in the first part. But yeah, I mean, really short, parity bits are just counting how many 1 bits you have in the message. So a parity, if it's 0, it means you have an even number. If it's 1, you have an odd number. And we went over the intuition of why multiple parity bits gives you more control over all the errors, right? So if you have only one, you can just, uh, with one parity bit, you can only measure like one, I guess, or something, I don't know. But with 3 parity bits, you can have 4 data bits, and you can correct errors in 4 data bits. So it's kind of doubled in size, and with other methods you'd get closer to 1 rate, but I think it would be way harder to implement 500 by 500 matrix multiplication than 7 by 4. So yeah, we just went with 7 by 4, which I guess it's kind of most usually used in um, some projects, I guess, I don't know. But yeah, so as I just mentioned, these columns were basically the positions from this table, right, that we were looking at yesterday. So for the encoding part, we just had to multiply our data with the G matrix. And from my testings from earlier, when I just trying to figure out how to do this stuff, what I found was that if we multiply H with the encoded message, we actually get back the syndrome. I Oh, I don't think it's mentioned here how to do the decoding. Maybe I'm on the wrong page or something, I don't know. But yeah, what I found was that if you multiply H with the encoded message, you actually get back the syndrome. And what can you do with this? So how this thing would look like probably is, imagine we have a matrix that's like well, it's just the you know, 0 1 1, or let me just make sure that I copy. Okay, 1 1 0, 1 0 1, and then 0 1 1, and then 1 1 1, 1 0 0 0 1 0 0 0 1. Right, if we, and here it's like, you can imagine it like two matrices concatenated, right? If we multiply this thing with our encoded message, we should get back 0 0 0 if the message is fine, and then we would get things like 1 0 0. That means that, oh, something's wrong, we have an error in our message. Or you would get, I don't know, like most probably you'll get like a combination of two, at least two numbers, because if you remember from last time, if you have parity bit 1, as if the syndrome is parity bit 1 is wrong and parity bit 4 is wrong, then you would go over these lines and find the intersection. So these two are both set, it means it's data bit 2. So in here you're probably gonna get something like 101 or 110. And if you notice, these results would actually be the first few columns, right? So the syndrome that you are gonna get from doing this matrix multiplication is gonna be one of these columns, or I mean it's gonna be 0 0 0, in which case you are good, but sometimes it's gonna be one of these columns, right? And how you can think about these columns is that this would be the first, like the most significant bit, so the bit I guess it's bit number 7. This would be bit number 6, 5, and 4. So the syndrome would give us like some kind of value, and we are going to check whether that value is equal to one of these columns. And if it is one of these columns, then it means that we have to flip the appropriate bit, right? So that's kind of the intuition on why the H matrix looks like it looks. I guess if you multiply it with the encoded message, you get back some value that gives you the index. So, I mean, hopefully that's not like really weird. I mean, I had to do a bunch of examples on paper to figure this out, but you know, if it feels weird, maybe I recommend doing that. But for now, you can just trust me. If you multiply H with encoded message, you basically get back either 0, in which case you are good, or the index of the bit that needs to be flipped. And of course, if you have multiple bits that are wrong, I have kind of no idea of how to fix that, so we'll see if we get into that. But for now, I just want to do single bit error correction. So yeah, let's try to implement this decode function, and then we are going to create like a really simple function that randomizes one bit or something to make it more realistic. So what we are gonna do for start is create the decoded nibble basically. So we are gonna say here byte, and let's call this one R. Okay, so this one needs to have how many items? I guess it needs to have 8 items. I mean, it needs to have 7, so let's just make it Hamming n just for now. So and as I said, we want to multiply basically h times r, right? And I mean, you know, it's in math, you'd say it's transposed, but we don't really care about that stuff. So we want to multiply h with this thing, so we have to build our entire matrix. I guess the easiest way to do that would be to set it as 0 for now, and then have a for loop, size the I is less than n, and let's just initialize. So ri is gonna be, so we want to do something like a byte. We want to shift the byte to the left, to the right with I guess Hamming n. So we want the last bit, so that would be Hamming n minus I, and we don't do -1 because we need the last one, and we end with a 1. Right, so this should give us all the bits from our encoded byte. And yeah, we just ignore the last one. So or I guess the bit number 0, we ignore it, we don't use it. So we just have the first 7 bits in here. So now let's do the matrix multiplication. So for the matrix multiplication, I guess we also need that x. Let's just have it here, maybe. So we do this matrix multiplication, and we are gonna get back, I guess let's call it S. And if you, this is gonna be the syndrome, right? So if we multiply a 3x7 with, I don't know how to write that, but with a 7 by 1, you get a matrix with size 3 by 1, right? And I mean, you know, the 1 is not important for us. We are not really doing math like really strictly. So we are gonna have an iteration over k, and here over n. We have the sum, and here we are gonna do basically h of j and I would assume. But I think we have to do ij actually. Ij multiplied with rj, and then we have to set si is equal to sum and all of that. Right, so we just multiply these two matrices. Hopefully that's correct. And we also need to maybe just compute something like let's say syndrome is equal to 0 for I is equal to 0, I less than Hamming k I plus plus. Let's just compute the syndrome just to make sure that it's either 0 or not, right? So if the syndrome is going to be syndrome, and let's say we are gonna add, so basically or si, and we have to shift it, so s at I, and we have to shift it by like Hamming k minus I. It really doesn't matter, we could just XOR all the bits, but I find this one to be a bit more cool. Okay, so here I need to do size t, and I mean this is gonna be also size t, but yeah. So if syndrome is equal to 0, we could just say something like printf no error, and let's just return, and we are going to initialize the nibble with the lower part of the bit so that we can print something, but hopefully we are going to see no error. All right, so that's going to be the goal. Right, so I guess we have multiple multiple bytes, so this would be like we would need 24, right? Because we have hello world has a size of 12, so this should be 24. I don't know how to actually count these. Anyway, it doesn't matter. It looks like 24. Like this would be 2, 4, 6. I mean, clearly it's 8, 10. Yeah, it's like 24. So because we would show no error for each nibble in the message, right? Okay, so that's nice. We don't have any errors right now because we haven't added that randomize function. We should maybe add it. So let's do like, I don't know, static void add 1 bit error, and this function, let's say it gets as input a bit, or it's a byte, so unsigned char pointer some byte, and it's gonna do some random error inside of it. So I'm just wondering where I should put it. So here we encode the message, and after we encode them, so I'm not gonna print all of this stuff, I think. I'm not sure. Anyway, let's do here something like for size the I is equal to 0, I is less than output length, I plus plus. And I like that we print these things. It's kind of useful to see them. But yeah, let's do add 1 bit error. Add 1 bit error, and we are gonna add this error on top of output at index I. Right, so we have, I mean, we could do plus I, but yeah. Okay, we could print these things again just to compare. Should we maybe print them in a single line and maybe have something like separator between them? Maybe that's gonna make it easier to see. Just thinking about it. I don't know. Let's just leave it like this. So how are we gonna add an error? I guess we need random.h or something. Is it random.h? Actually, I have no idea. Okay, let's srand first. Srand, and usually do time null, right? Time.h, obviously. Also, this is stdlib, nice. So let's say that we are going to add 1 bit error if random, so this is a random number between 0 and random max, so we could change it to, let's say, double and divided by rand max, and if this thing is less than 0.5, or I guess larger than or equal to 0.5, we are gonna add 1 bit error, right? Yo, hello, I'm doing error correction for our steganography tool, so it's gonna be basically having the code today, and we'll see what we can do after that. But yeah, okay, so we have a single byte here, and honestly I'm gonna add the error just in the first 4 bits. So if yeah, because why not? It's gonna make things easier for us, hopefully. So we want an index, so let's say size t index, and this one is gonna be also a random number, and I want to modulo this thing by basically Hamming carry, because that's the amount of data bits that we have. And after that, we need to do something like star byte. We need to shift, not really, we just need a mask for this thing. Right, so how do you actually like reverse a bit? You do XOR on top of it, right? So we have to XOR this thing with like a 1, and we need to shift this one to the left by 8 minus in. So if we think about it, index is going to be a number between 0 and 4, or I guess 0, 1, 2, 3. Then we shift, we have 8 minus 3 is 5, so we also have to do minus 1, obviously. So maybe this is going to be Hamming n minus index, and that would be what we need to do to byte, just to shift, just to flip one bit. Basically we want to flip a bit to come up with an error, basically, like just add a random error in here. Let's see if that actually inserts an error. So yeah, as I said, I think I want to put them on lines because it's gonna make things a bit easier. Oops. So maybe I want to add an extra space between them, but then a new line at the end. So something like this I think would be nice to visualize. Okay, so if we look at this stuff, I don't really like, no, it's fine, it's just the line wrap, which is kind of weird, but whatever. So we have this one is the first one. This one you can see it has a flipped bit, so this one contains an error, right? The second byte. Then this one, I think this one also has a flipped bit in here. This one yeah, it also has a flipped bit, but it's fine as long as these 3 bits are not flipped. Then I'm good, to be honest, because I want to keep them fixed for now. We don't want to have errors in here. It's kind of like, it should be easy to solve. It's the same, I mean, it's the same algorithm, but yeah. And as you can see, there are only like these 3 without an error, like W. This would be hello world, but right now it's broken, right? So we have to fix it. Okay, perfect. So we have this dummy, like insert dummy error, and we want to basically fix this dummy error with some bit magic. So if the syndrome is 0, we just return, we don't do anything, but otherwise we need to fix this, right? So let's figure out, as I mentioned in the beginning, the syndrome code is going to give us which bit we need to flip, right? So we just need to iterate over h and figure out which column is equal to our syndrome. So let's do a for loop over n. So I'm just gonna copy this one. So it's gonna be 4, and here is gonna be n, and n is the one with number 7. Yeah, perfect. So this is gonna be our thingy. Nice. Let's have something like int matching is equal to is 1 maybe. So we first of all assume that this column matches the current syndrome, and then we need a for loop that goes until having k. Okay, and in this one we just need to compare the s array with h. So if s at index j is not equal to h at ij, then we need to break. Matching is equal to 0 and we break. Right, so that's not the right index, that's not the right I. So I'm gonna have here something like size t index. Let's make it 0, it doesn't matter. But if matching is equal to 1, then index is equal to I and we break. And this kind of needs to happen. Like at some point we are gonna get some index, and hopefully it's gonna be, you know, I don't know, 0, 1, 2, 3, 4, 5, 6, right? It's gonna be one of these columns. So maybe let's first of all print the index, print f, flipped index, and let's do like percentage zu, new line, and let's print the index. So hopefully the index, some segmented, flipped index 1. So at least for this one, we can see that it's right. Flipped index is actually 1. But what? That's interesting. So for the second one, it's just segmentation fault. But I think, yeah, this one is also flipped, so it should also say it's flipped, but what the fuck? I mean, where did it segfault? Actually, I have no idea where. Let's use Valgrind because that's gonna show us where the error happened. So on line 83 here, the fuck? H. So I guess we need to swap these two. Is that true though? KK, yeah, we had to swap them because J is basically the row and I was the column. Yeah, whatever. I mean, matrices. Okay, let's run this again. Flipped index 0. Okay, now it's wrong. Shit. Let's maybe print f percentage zu syndrome. I'm curious, maybe I didn't compute it the right way. So it's 1, 6 doesn't look right, to be honest with you. It should be like, if you think about it, 7 is the greatest value it can have. So, oopsie. That's interesting. Let's just print f the z values, or I guess the s values. Si. Here's like what? Wait. It's a character. Okay, so it's gonna be d or something. Okay, why are there 4? The fuck? Hamming, oh shit, I have to do Hamming n minus Hamming k. Yeah, I have to do this d thingy. So here s actually has this size. So it's Hamming n minus Hamming k. And here we are just iterating over these three. As I said, we have a 3 by 7 matrix here. It's yeah, my bad. So we have Hamming n minus Hamming k. Here the same. I is right. S. Then we have Hamming n minus Hamming k here as well. Maybe I need to create a constant like Hamming d, because that's what I saw it's called on Wikipedia, but it's fine. So this should be the actual stuff. Okay. So now it looks better. It's like 7, and here it says the flipped index is 3. Let's see if it's actually 3. I guess the first one is not flipped, so we can ignore that. This one, it's also not flipped. What? Here is this one is the first one that's flipped, so it's 1 0 1 2 3. That's right. And it kind of looks fine, like all the numbers make sense, honestly. Yeah, here you can see that these 3 are zeros, then these 3 are also zeros, so they are all good. Also zeros, then all ones, and all ones means index 3, because if we check in here, all ones is the third column, right? So in our H matrix, all ones is the third column, so 0 1 2 3. So it's the third index that's flipped. So that's kind of the intuition. Here you can see it's 1 0 1, and that is this column, which means which is a 5, right? It's a 5, and it means it's 0 1. It's weird. Let me just double check where I have 1 0 1. Well, I mean here I have 1 0 1 in the yeah, it's fine. 1 0 1 is this one. All right, so it's this one. And then we have like what, 1 1 0. In my matrix, 1 1 0 is the first index, so it should say 0. 0 1 1 is this one, so it's the second index, so it says 2. And all of that looks good, honestly. So let's remove these prints. So here we know which index needs to be flipped in our byte. So let me just take this thing and move it here. It makes more sense to see it here. So if we don't have an error, we just get a byte. But if we have an error, we need to flip this index, and we already know how to do that because we did it here for the error. So let's flip. So we are gonna do something like byte is byte, and we flip the index, right? And after that we can just take the nibble and set it like this. So this should be the entire thing. Like this should give us the corrected message back, and we actually get back hello world. And I think that's kind of cool that we have like a noisy message with errors inside of it, and we actually get back the original message. So I think that's like absolute coding moment. Here we are doing like encoding a string message, or I guess, you know, binary message, something that you would send over the network, and we add some error correcting bits to this message, so that after we insert some dummy error, you know, it could be caused by networking stuff, it can revert and figure out what was the original message. So that's what we are doing here. Okay, so I think that's kind of nice. Now obviously we could have the error go like full up until n. It doesn't really matter. I'm pretty sure it should work. Yeah, so even if you have errors in the correcting bits itself, it still works. What I think it doesn't work though is if you have 2 errors. So if you do 2 errors, it might not work. So, but let's just see what would happen if we have 2 errors. Yeah, so if we have 2 errors, or I guess 2 flipped bits, we cannot really figure out what was in the message. So that's kind of how Hamming code works. So yeah, I mean, that was everything we wanted to do here in Hamming the code. There's also, I guess, just a second, okay, so all's good. Nice. There's also this thing which is called 8 for Hamming code, which kind of gives us the possibility to see if the message has 2 errors, but we still cannot fix them. We can only fix 1 bit errors. That's kind of useless possibly, so let's just leave it out for now. So now that we have this thing, let me just commit this thing, feature add decoding. So as I said, we are implementing this thing for the stack tool, and last time, if we check the stack tool, I added here, off screen, I did the error correcting part, but just for the encoding. So the goal would be to just copy paste that stuff in here, maybe try to use it, see how it would be used in a real case. So let me just copy paste the H matrix. I haven't added it in our stack tool, so let's just add it. I also want to add the entire decode function. All right, so the decode helper. Decode. Okay. And here we have the Hamming decode and Hamming encode. So this should be everything that we need from this file. I mean, the random error, we don't really need it, honestly. We might create like a bash script to test that, but it's not important. Okay, so with this error correcting thingy, so error.h has Hamming encode and Hamming decode. We can go into the main file, and let's say we only do this for the lsb command because it's gonna be a bit easier, or I think it's most useful for the lsb command. So in the lsb command, we are hiding a payload in an image. So I guess if you haven't seen this stack tool before, it's like hide dct. We are okay, so let's say we hide I don't know, 16 A's inside of this image. So this image is just lena.png, but we basically hide 16 bytes inside of this image, right? And the goal is the image obviously kind of looks the same. It has some artifacts for DCT. I guess that's just how DCT works. But if we try to show decode the image, we get back the actual bytes, right? So it's like storing information in an image without making it obvious or without changing the image that much. So the image stays kind of the same. It's not noticeable to the human eye, but it actually contains information, right? And the problem with this is that if you, I don't know, send the image over WhatsApp or some network, it could add some error bits inside the image. And obviously these tools have some kind of error correction for the pixels, like such that the pixels look good, but maybe they don't have like perfect error correction over the bits from the image. So maybe the bits of the image are gonna be a bit different, but we want them to be exactly the same because, you know, we have a string message in there and we want it to be decoded properly. So we could add our own error correction algorithm, and I would do that. I'm not even sure if I want to do it in the command line itself or I want to have a separate command for it. Like, I think maybe we want a separate command because first you'd take the message, you apply error correction on it, and then you hide it. Right? I don't think, or maybe it should be part, like it's gonna make it easier if we make it part of the hide command. So yeah, why not? Let's just do that. Let's just put it inside of the hide command, but let's have something like boolean error correction code. Let's call it ECC, and let's, you know, add a comment, use error correction. And I mean, the downside of using error correction is that it doubles the size of the payload. So that's the only issue with, I would say, with error correction. So let's do E. Let's call it ECC, error correction code, and error correction, or I guess, you know, use error correction, and the default is gonna be false. And the argument is type flag. Perfect. So let's do something like args.ecc, and let's parse. Let's do actually get flag, and here we're gonna pass the parser and ECC. Okay, so after we here we read the image, obviously, then we read the payload. But what we are gonna do is, if args.ecc is true, we are going to do something like inside of error.h we have Hamming encode. So Hamming encode, it should include error.h. Perfect. We are gonna pass in the payload. So payload, we are gonna pass in the payload length, and then we want to output a new, wait, just wanted to see instead of error C, we allocate a new array here, right? So we malloc something, yeah. Okay, so let's pass in a new thingy here. So I'm gonna do something like const int 8d encoded is gonna be equal to null. So let's send it here. So encoded, and maybe size t enc length, let's make it 0, and let's pass it here, enc length. This should be just unit 8. Okay, now thing is, I don't want payload to be const because we are gonna mutate it here, but this thing can fail, right? So we have some SEC result. So if this thing is not equal to ECC OK, then we just exit failure, and we are gonna, I don't know, AIDS log, AIDS error, error encoding the message with Hamming code. And then, I mean, we don't have a reason, but it just failed. Probably, I don't know, malloc or something failed, right? That's kind of the only reason it could fail. Okay. Otherwise, we want payload to be equal to enc, but we also want I guess I wanted to free the payload at some point, but honestly, it's like it's not really gonna be leaking memory because it just exits at the end, so it's not really the case. But I would say that here you want to free payload and then assign enc to it. Right, so I don't know, I would do something like ds free payload str, right? So we want to, or I mean, it's just payload. Wait, what? Is it not? Yeah, it's just free, right? Oh yeah, whatever. We can just free the slice at the end if we want to, because here IO read is gonna put some stuff in the slice, so we can just free the slice. There's no problem. Yeah, I mean, maybe it's not right to make it const. Okay, let me just do it's free and payload. Like it should work, right? And then we put the stuff, and payload length is gonna be enc length. Nice. So that's just gonna add some extra stuff like the encoding, and then obviously at the end we also want to do something like if payload is not null, we do free on the payload. Maybe we also set, I should get more into the habit of setting the pointers to null when they are freed, otherwise it might be confusing. But yeah, like this should add encoding to our LSB. Okay, and let's also add encoding to the decoder, like use error correction. So let's copy paste this stuff into here to use error correction. By default it's false, and then we want to add this one here, and after we do show LSB, we need to apply the error correction. So let's just copy paste this if statement, and I'm gonna put it here as I said. So here we want to Hamming decode. We want to decode our message. So we're gonna pass the message here and message length, and let's rename this one to decoded, so dec, and this one is gonna be decoded length. Error decoding the message with Hamming code. I think this also allocates the A array, so let's just free the message here, and then we're gonna set the message to dec, and then message length is gonna be dec length. Oh, I mean, it has the funny name dec length, but it's not unfortunate, right? It's one letter away from being not great. Okay, So here we free the bytes. Let's set also bytes to null, just in case. And we also set the message to null, just in case. Okay, so that should add encoding and decoding, right? So, and as I said, this is gonna make the messages larger, but at least we're gonna have error correction. So it's not, it's more, how can you say that? It's like more robust, I guess. Let me say it's more robust. So that's kind of the point. Okay, so let's try to now use this thing. So if I run make, did I forget to, yeah, I guess I forgot to update the makefile. So makefile, here we need to add build dir slash error.o, and let's add error.o. It wants error.c and error.h, and it should compile now. Perfect. So now if we hide lsb, if we are trying to hide interesting, no position argument available. Maybe there's something wrong here. So it wants minus o output and then the image. Okay. So it's minus o here. But I think I want test bin to be like hello world, exclamation point. Okay, so let's hide the message, and then if we check Lena out with LSB, honestly, it looks like it looks the best in my opinion, but I don't know. Okay, and let's try to also use ECC, like error correction. Still works. Let's just check that the image looks the same, kind of the same. I don't see any problems. Obviously the problems would appear in the top left corner because that's where the encoding starts. Like that's the idea. But let's now do show LSB, and if we don't do error correction code, it's gonna be broken. It's gonna be like, I don't know what that is, because it's the encoded message basically, right? It's not the decoded. But if we add ECC, it should say hello world, because now it also applied the decoding over the message, right? So that's kind of the idea here. If you use ECC in the encoding, you have to use it also for the decoding part. Okay, I mean that's kind of cool. Right, so this would add an extra layer of protection, let's say, on the messages. I think it's kind of nice. Something else that would add another layer of protection would be maybe like some kind of encryption, maybe using a XOR key, or I don't know, something like that. Honestly, yeah, I think that's good enough though. Just error correction code. I mean, even with the error correction code, it's also kind of encrypted, because as you can see here, if you don't use error correction, it looks like gibberish. So I mean, that's still something nice. But you know, obviously you want something more, something better. So what should we do in that case is read the payload, apply that encoding, or apply that algorithm for like encrypting the payload. Then we apply ECC. Then in the decoding part, you need to keep the order right. So you first show LSB, then I think you have to apply ECC first, and then you decode, right? So you have to keep the order the same, or I guess invert the order, right? Invert the order of operations. So that's kind of what we would do with, I don't know, like XOR key or something. Okay, let me just, I'm curious if this thing actually works. Like, is Valgrind happy with this? I guess it is. Nice. And is it also happy with the LSB? Nice. Okay, so we are properly managing the memory. Nice. Usually it's a good idea to do memory management from the beginning, otherwise it's gonna be hard. Or at least document where you allocate memory so that you know what you have to free. But in any case, so yeah, we also added error correction to the stake tool. Now I'm thinking, how can we maybe try to break this thing? Can we have like a really simple script that would break the image? Maybe let's add an extra command. Noise LSB or something. So this would simulate noise in an LSB encoded image, right? So let's just add it here. So we add it at the end, command noise LSB, and the idea is command noise LSB. I don't think I want, I mean, actually I want arguments, obviously, but we'll see what we need. So here, oops, stag noise args LSB or something. So we want the image path, output path, probably compression level as well. That's fine. Let me just actually copy paste this thing. So we want the image that we path the image path to save the modified image. We don't have any payload. Compression and error correction, it's not important. Okay, so these are the arguments that we need, right? So let's go up here and let's just copy paste this part. That's what we are gonna need. So in here, let's just copy paste this part. Simulate noise in LSB. Command noise LSB. Fuck. Yeah, whatever. So here we get the image. So that image, the payload, I said it's not important. Compression, I would say maybe, because we want to modify only, I want to modify only one bit, so probably it's not important, but let's just keep it there. Maybe we are gonna use it, I don't know. So at the end is return 0, and what we want to do is probably load the image. So let's do stbi load. Right, we load the image, then we want to obviously free the image at some point. So here maybe also set bytes to null, but we want to free the image at the end. And now let's just say that we kind of use the same logic that we did in our add 1-bit error. So let me just copy paste this function here just to have, you know, inspiration for it. And also something that's important, probably it's this srand thingy. So let's actually add this thing first. So we are gonna srand, and we need to include time.h. Okay, and then we want to insert dummy error. Okay, so for inserting the dummy error, we want to iterate the image until width height num channels, width times height times num channels. And if we have, now that's the interesting part. We want to insert only one error per 8 bits, so that's why we need the compression for. So that means we want some kind of reset index. So how can we do that? Anyway, it doesn't matter that much, but let's just say we have this thing, right? The index where we want to add the error is gonna be args.compression level, or I guess modulo. This is gonna be the index, and we want to modify a byte. So Hamming, this should be, so let's think. Here is just index actually, and we want uint 8t byte to come from the image, like that, and then we just set bytes at I equal to byte. So this is gonna randomize, randomly one of the bytes from the least significant bit. It's gonna flip one of them, right? So with this approach, it's probably not gonna work because it's gonna be too many errors. So that's why I want some kind of okay, so I know what to do. So instead of I++, we're gonna do I plus, let's do size t stride. The stride needs to be, we don't have byte size, but it's 8 divided by args.compression level. So this is gonna be the stride. So we need to increment by stride. Nice. Now let's choose, let's still have a random here, but now let's choose size t byte index is gonna be random modulo stride. So here we choose a byte, or I guess one of the bits that we want to modify. So here we choose byte index. So this is gonna be random modulo stride, so I plus, right? And here it's byte index, and this is gonna be, it's basically the bit index, but yeah. So here it's I plus random modulo stride. So this should flip some bits. Right, so let's do a make. What happened? These are integers. Let's convert all of these to size t then. So I think this should be good. Okay, so if we now hide this thing, the image should look the same. But now if we do build stag noise lsb, oh, I forgot to save the image. Okay, so let's also save the image. So after we are done, we should just save the image. I forgot about the most important part. Okay, so we are gonna do output path, we save the image, messy, or I guess noise added successfully. Okay, so let's do make again. So if we build stag noise lsb, and we take Lena out and we output, wait, is this one, how is this working? Okay, so it's -0, Lena out, and we output into Lena out png. We added some noise, the image looks the same, right? But if we show LSB with ECC, it should still find the message, or I guess not. You know, maybe I did something wrong in here. Let's say we only break, yeah, we only destroy one bit or something, like we break afterwards, just to make sure that, you know, if we break one bit, it still works. So if we hide, then we add some noise, and then we try to show LSB. Still broken. Wait, so in hide LSB, we do hide LSB, and then we write. It should work. Maybe let's print f %zu index I, and let's see where that error like where did we place the error. 0. It's funny. And what is byte index? 32? The fuck? Wait, how is byte index 32? Ah, okay, I guess maybe I was a different value this time. Let's do again hide LSB. Let's but even then, if you know, it's fine. If I was a different value, then yeah. Let's do some noise, and if we try to show LSB, interesting. Let's start with, I don't know, 100. Let's try to hide, then we do noise, and then if we do show, now it's fine because it's way too big, to be honest. But it's interesting, why doesn't it work? Because it looks like it's not breaking that much, to be honest. I mean, the stride is gonna be 8, so it's not even that important. Hello. So yeah, I mean, it's this thing should add some errors in our message, but I'm not sure why it's not parsing the thing properly afterwards. So here we apply, if we have error correction code, we encode it, correction show LSB, is doing decode length, Hamming decode. Yeah, that's kind of weird why it doesn't work. Insert dummy error. I mean, we do the error the same as we did in the other one, so yeah, I'm not sure why it's what it doesn't like about this this error with compression level 1. Maybe the index is not right. So index is gonna be basically always 0 if we think about it. So I'm doing 1 shifted by 0. So yeah, I mean, if I would print this thing, it should always be 0. Maybe without this one, just in case. And if we do noise, it's always going to be 0. It's nothing it can do about it. So it just flips one of these things. In no 8, and then another 8, and so on. So it should be good. It's kind of weird. Oh, so here it's by, maybe I'm dumb about this one. Maybe it's something that's not aligned properly. Let's just do like a comment there. Let's do the hide one first. Noise, and then show. Shit. So it's like, okay, minus O output B. So it breaks the length, the encoded length. It breaks it for some reason. Why, I have no idea. So when it hides like the text message, it's all good, but when it applies it for the length, it doesn't work. So I have no idea why. Well, I guess I know why. It's because here we apply ECC only on the payload, but we don't apply ECC on the length itself, right? So we apply ECC only here, but we don't apply ECC here. So maybe we want to, apply ECC on the payload length as well. Okay, then I guess just to avoid that issue, we know that the payload length is 8 times size t of size, or I guess size t. So we know that this will no longer break it because yeah, we don't apply error correction on the length itself. We only apply error correction on the payload. So let's just do it like this for now. So this should work now. I'm gonna add ECC on the length myself, but for now let's just do like what to do here. Add ECC on the length as well to avoid this. Okay, so here we can resume randoming, and let's just do a bunch of printfs to know where this byte index, maybe also %zu for I. But yeah, this should add a bunch of errors now in the image. So if we do hide LSB and then we add some noise, I mean, you can see it's a bunch of errors. And if we show, we still get hello world back. And the image looks kind of the same because yeah, but I mean, that's kind of the point of this thing. You can just flip random bits in the encoded image, and with the error correction codes you still get back the original message even if the image was altered afterwards. So that's kind of cool. And as I said, I have to fix the beginning of the payload, but that's something kind of yeah, sure, I mean, kind of makes sense to add it, but yeah, I'll try to do it on my own. But yeah, that's kind of the point of error correction codes, right? So hopefully it makes sense why you would want to add them in your like if you do anything to do with networking, probably. But obviously I would say most libraries would have them included or something, like I would assume. Probably like protocols, network protocols, they have this kind of error correction in them, because as far as I know, TCP, if it detects errors, it requests the packet again or something, so it already detects errors, right? But there are UDP doesn't do error correction, so that's also something. But yeah, this was interesting. I mean, there are other algorithms as well, but I don't think that's I mean, you should just know that they exist, and as long as you can implement them from the Wikipedia page, or I don't know, you can ask ChatGPT to help you. It's pretty simple, but yeah, I mean, it was kind of interesting. Maybe I would be interested to look into this 8.4 algorithm, but that's something I need to prepare a bit for. But yeah, this was kind of everything I wanted to do for today. So I don't know if you have any questions or anything, you can leave them in the chat. So yeah, we also added this command to add some dummy errors. Let me just show this. Add noise in the LSB of the image. So I mean, I think the project itself is in the description, so you should be able to check it out. To LSB. Yeah, so as I said, this was all for today. Thank you everyone for joining, and let's see the next one. Until then, see you.